short. I just shorted Bioverativ, which, like I said, is a pure play company that makes just factor 8 and factor 9. They don't have any of the gene therapy products. So gene therapy is what's happening here. These 4 companies are all doing gene therapy. And there's another drug called emicizumab from Roche, which actually also is going to hurt all of the legacy factor 8 and factor 9 companies. So in many ways, the companies that make money on factor 8 and factor 9 are going to have big problems in the next 5 or 10 years because nobody's going to use these products anymore. And nobody wants to use these products anymore. They're very inconvenient. They're very frustrating. And, I think that it's sort of like I don't know, dial-up versus broadband or something. But, in essence, there's a huge sea change that, again, you rarely see in medicine. So what is gene therapy? Somebody asked in the chat. Well, gene therapy, traditionally, I've always been skeptical of gene therapy. The idea of gene therapy is that you load a virus. You load some kind of virus, and you call that a viral vector. And you load it with a transgene. So I don't have my stylus with me, but I used to do these in the old streams, so we'll get a throwback. So you have, and I'm the worst artist ever, so I'll do my best here. But you try to load a transgene, and so this is sometimes called the POI, or protein of interest, and so this is what you're missing. The patient is missing. So it could be something like factor 8, and you take that transgene and you put it in something called a viral host or a viral vector. And a lot of people have been doing something called AAV. There's sort of 2 general approaches. There's AAV and there's lentivirus, and you can pick your poison literally, I suppose, because these are real viruses. In fact, AAV infects a lot of people in the United States, and there's different serotypes, of course, of every virus. So each serotype, this is terrible. I should really get my stylus. Each serotype has a tropism. I didn't plan to go into this detail, but because you guys are curious, I'll happily do it. Tropism is a sort of affinity for a tissue type. So there's certain pretty interesting AAV serotypes that are have tropism for different parts of the body. So you can have AAV, say 5. I know some of the guys like AAV 5. You can do AAV 9 for the brain, and that's one company I'm focused on called Avexis. So anyways, what's important to know about these viruses is that the AAVs are non-integrating. So basically what they do, they're non-integrating. They do not change the germline DNA. So they don't go in there and actually edit the DNA. And I actually think that's a good thing, because if you try to do that, you'd end up with a host, no pun intended, a host of problems. So what they do is they form these concatameric, I hope that's spelled right, concatameric episomes, which are not, they're not even in the DNA, so to speak. They kind of form these weird, the AAV will go into the cell. How it does that is its own can of worms. So here's a cell. So the AAV sort of gets in there, and I want to say in some cellular compartment, it's probably some ribosomal compartment, the concaromatic episome is formed, and what you end up having is read-through that creates production of sort of this protein of interest that will get created, and then all of a sudden the patient can make factor 8. Now in the actual germline DNA, the normal DNA is not being changed, so it's a sort of separate side DNA that's being created, which is kind of interesting. Now in lentiviral gene therapy, you actually have an integration, and that's sort of, I think, more dangerous. Now with both of these, you have something called the viral capsid that gets that gets stuck in the cell, and that can become immunogenic and actually result in antibody destruction. So you have to be very careful as to how you pick these things. And one of the things that you worry about with gene therapy is the long-term viability of it. The reason I never liked gene therapy has to do with sort of transgene efficiency, or transduction efficiency. And in essence, what happens here is no matter how many viral particles you give, you actually can't get every cell in the body. But one of the crazy things about the body is we have a liver. And the liver does a great job of getting all of the blood to flow to it through something called the portal vein. And because of that, and because of the way that liver cells called hepatocytes are organized, gene therapy transgenes get stuck in hepatocytes very easily. And it turns out that hemophilia is a liver protein. So your livers create the hemophilia protein. You can imagine that maybe your brain creates dopamine proteins and GABA proteins and things like that. Well, the liver creates hepatocytes. The liver's hepatocytes create factor VIII and factor IX, which is why gene therapy is particularly good for liver diseases like hemophilia. So in essence, that's how sort of gene therapy works. And I'll show you some results in a second. But in essence, these 4 companies are all making AAV vectors to change hemophilia. So again, just to wrap up here, if you had this concatenameric episome that created the factor VIII and factor IX, maybe it gets secreted, and here you have factor VIII swimming around. So we'll just call it F8, swimming around, and it sees a damaged blood, and it says, hey, I'm going to go clot that. I'm going to go help clot that and restore order, and don't let that bleed grow or continue to bleed. That's sort of what's going to happen if that concatenameric episome can get read through to actually create protein production, which seems to happen. We'll show you that data in a second. Because don't forget, just because you get the virus to infect the cell doesn't mean you're going to actually get that protein to come out. Because the virus infects the cell. Maybe the cell gets destroyed, not due to the virus. The virus is pretty harmless. It's actually maybe due to the immunogenicity that the body says, hey, I know you, you're a virus. I see your capsid right here. I'm gonna kill you, and that ends up eliminating the cell, and you don't get the factor VIII, and you don't get the anti-hemophilia cure, and you don't get the billions of dollars. And the very happy patients, of course. But so we'll see about that in a second. But obviously, you can also just make the recombinant factor VIII. That's what these companies do. They create recombinant copies of factor VIII. You take them by IV infusion, so you don't have to worry about this whole, gene therapy nonsense. Now, the nice thing about the gene therapy is that this cell will persist, and it'll keep making factor VIII all the time. So you never, maybe, hopefully, never need to get a factor VIII infusion again. So that's the basics of gene therapy. That's the basics of hemophilia. So my theory and my thesis is that gene therapy will eliminate the need for recombinant factor VIII and IX, and these $8 to $10 billion business will vanish, and that from these companies, and it'll go to these companies, and maybe even more. So you have, interestingly, Sangamo is they all have partnerships. So Spark has a partnership with Pfizer, and I think Sangamo has a partnership with Pfizer. So Unicure and BioMarin don't have partners. So in essence, that's I'm not long Pfizer, but it's important to know that these companies have a deal with Pfizer. So Pfizer's at least said, I'm not going to let my lunch get eaten. I at least want to kind of, partner up with one of these new hotshot companies and at least share the meal with them.